Good day, Doctor. Before I begin the presentation, I would like to briefly introduce myself. My name is KIB2014 and I'm presenting together with my group mates Farzana Azian binti Faisal, Zamil Asif bin Zamri and also Lim An Leong. We are from Group 1 and this presentation is for our KIB2014 Numerical Method and Programming assignment. Now, let's look at the abstract of this assignment. Systems of linear equation are widely used in engineering application. As problem size increases, efficient numerical methods are required. This project implemented Gauss elimination, LU decomposition, and PLU decomposition method using C++ and MATLAB to solve simple, intermediate, and complex systems and compare their performance. Now, let's move to the introduction. First, I'm going to explain about the general introduction. So the system of linear equation play a crucial role in engineering analysis and mathematical modeling. This project examining Gauss elimination, LU decomposition and PLU decomposition to compare their efficiency and numerical stability when solving linear system in engineering application. Let's move to the method introduction. The first method is Gauss elimination method. The Gauss elimination method solves a system of linear equation by converting the argumented matrix into an upper triangular form. This is achieved through forward elimination, where coefficients below the main diagonal are eliminated, followed by back substitution to compute the value of unknown variable. Next, we move to the second method, which is LU decomposition method. LU decomposition expresses a square matrix A as the product of two matrices. A equals to LU, where L is a lower triangular matrix and U is the upper triangular matrix. The solution process involves forward substitution to solve Ly equals to B, followed by backward substitution to solve Ux equals to Y. Next, our last method, which is PLU decomposition. Standard LU fails when pivots are 0 or very small, which is the division by 0 or numerical errors. PLU use partial pivoting, or also known as a row swapping, to place the largest pivot on the diagonal. Introduce a permutation matrix P, giving the equation of PA equals to LU. So now let's look at the solution step. First is decompose, where A becomes P LU. Forward substitution. So the equation is Ly equals to PB, and the last step is back substitution. The equation is Ux equivalent to Y. Now let's look at the problem statement. For the scenario 1, which is a simple case about infusion pump calibration and dosage control. Infusion pump require precise calibration to ensure accurate drug delivery and patient safety. During calibration, sensor readings are modeled using simultaneous linear equation to determine unknown calibration coefficient. Calibration coefficient, we assume X equals to flow rate calibration factor and Y equals to pressure sensor calibration factor, Z is drug concentration calibration factor. Calibration model, which is the linear system, we have three equations. The first equation is 2x plus y plus z equals to 9. The second equation is x plus 3y plus 2z equals to 13. And the last one is 3x plus y plus 4z is equivalent to 16. Since multiple measurements are required for reliable calibration, numerical methods such as Gauss elimination and LU decomposition are used to efficiently solve the system and obtain accurate calibration parameters.
Hi, I'm Farzana Azian, matrix number 24040065. So this slide presents the intermediate case, which focuses on biomedical signal reconstruction in a multi-electrode EMG system. In a multi-electrode EMG system, muscle activity is recorded using several surface electrodes. However, each electrode does not measure a single muscle independently. Instead, due to volume conduction, signal overlap, and crosstalk between adjacent muscle, each electrode records a mixture of signals from multiple muscles. Because of this overlap, raw EMG signal cannot be directly interpreted as individual muscle activation levels. This makes it difficult to identify the contribution of each muscle from the measured signals alone. Therefore, mathematical reconstruction is required to estimate the true muscle activation. The EMG system can be modeled as a system of linear equations in the form AX equal B, where A represents the electrode muscle coupling coefficient, X is the unknown muscle activation vector, and B is the measured EMG signal vector. For this case, three surface electrodes are used, resulting in a system of three linear equations as shown. The variables x, y, and z represent the unknown muscle activation levels. Since EMG measurements are often repeated using the same electrode configuration, an efficient solution method is required. Therefore, LU decomposition is applied to factorize the coefficient matrix and solve the system efficiently using forward and backward substitution.
Hi, my name is Zamil Hasif. Now I'll explain about scenario 3, which is a complex case. For the problem statement, we have chosen the fabrication of injectable hydrogels for cartilage repair. Articular cartilage has a limited capacity for self-repair due to its lack of blood supply. Consequently, biomedical engineers are developing injectable hydrogels that can fill irregularly shaped cartilage defects and polymerize in situ to provide mechanical support. A leading material for this application is alginate, a polysaccharide that forms a hydrogel when cross-linked with a calcium ion. However, the properties of the final gel are highly sensitive to the mixing ratio of its component. The hydrogen must be stiff enough to withstand joint loading, yet porous enough to allow nutrients diffusion. We are designing a smart mixing system for a surgical tool that blends 3 liquid precursors during injection. We must calculate the exact flow rates required to achieve a hydrogel with specific mechanical properties. The 3 precursors is X1, flow rate of phosphate buffered solid, X2, flow rate of sodium alginate solution, X3, flow rate of calcium chloride, the cross-link. So the governing equation is what you can see in the slides. So why we use PLU? We use PLU because standard Gauss elimination fails here because it tries to divide by the first pivot, which is 0. So it will try to divide 1 over 0, which will give an error. Therefore, we must use PLU decomposition, which is LU method, but with partial pivoting. This method allows us to swap row 1 with row 3 to move a non-zero number to the pivot position, solving the system without crashing.
For the input, two input methods were used for solving system of linear equation. The first one is manual key in, allow direct entry of equation coefficient for small problem sizes and quick testing of numerical method. Second is text file input, used for large data set, improve efficiency, reduce input error, and support structured data processing. Both methods enable accurate and reliable numerical computation using methods such as Gauss elimination and also LU decomposition. Now let's look at the pseudocode. So for the C class, we have the pseudocode here, and this will be explained in the discussion part. This is the algorithm for the MATLAB, and this is also will be explained in the discussion.
Now, this slide shows the pseudocode implementation of the LU decomposition algorithm used to solve the EMG intermediate case. The program begins by defining a procedure for LU decomposition where the coefficient matrix A is decomposed into a lower triangular matrix L and an upper triangular matrix U. Initially, L is set as identity matrix, while U is initialized as a copy of matrix A. Next, quotient elimination is applied. For each column, the elements below the pivot are eliminated using a multiplication factor. This factor is stored in the corresponding position of matrix L, while U is updated through row operations. As a result, the original matrix A is successfully factorized into L and U. Once the decomposition is completed, the system is solved into two stages. First, forward substitution is performed to solve the equation Ly equals B. In this step, each element of the intermediate vector y is computed using previously calculated values, taking advantage of the lower triangular structure of L. Then, backward substitution is applied to solve Ux equal y. This solution vector x is computed starting from the last equation and moving upwards, which is possible because U is an upper triangular matrix. In the main program, the system size is set to 3, corresponding to the 3 electrodes EMG case. The user inputs matrix A and vector B either manually or through a text file. The program then subsequently calls LU decomposition, forward substitution, and backward substitution. Finally, the computed values of X, Y, and Z are displayed, representing the reconstructed muscle activation signals. This slide presents the MATLAB-style pseudocode used to solve the intermediate EMG case using LU decomposition. The program begins by reading the system size n, followed by coefficient matrix A and a measured EMG signal vector B. These inputs together represent the linear system AX equals B. Next, the matrices are initialized. The lower triangular matrix L is set as an identity matrix, while the upper triangular matrix U is initialized as a copy of matrix A. The LU decomposition process is then performed using nested loops. For each column K, the elements below the pivot are eliminated using a factor calculated from the ratio of UIK to UKK. This factor is stored in the corresponding position of matrix L, and matrix U is updated through row operations. At the end of this process, the matrix A is factorized into L and U. After decomposition, forward substitution is applied to solve the system Ly equals B. The intermediate vector Y is computed sequentially using previously calculated values and the lower triangular structure of L. Next, backward substitution is used to solve Ux equal y. The solution vector x is calculated starting from the last equation and moving upwards, taking advantage of the upper triangular structure of U. Finally, the solution variables x, y, and z are assigned from the solution vector x and displayed as the reconstructed muscle activation signals.
Now let's look at the pseudocode for PLU decomposition method. This pseudocode will be explained more in detail in the discussion part, but I will go through them briefly. So for C++, the pseudocode starts by initializing. Then we start the loop for k equal to 0 to n minus 1. We search for a pivot. If the maximum absolute value is equal to 0, then we print error system is singular. If not, we start with the row swapping. After that, we go through the step of elimination, then forward substitution, then back substitution. After that, we show solution vector of x. After that, we end the program. For MATLAB pseudocode, it is almost identical to the C++ pseudocode. Firstly, we start the program by opening the file of complex_data.txt. After that, we initialize the matrix L and P and also set U is equal to 0. Then we start with the decomposition loop for k equal to 1 to n minus 1. For a decomposition loop, we start by pivot search. If maximum value is less than 1 e to the power of negative 9, which is equal to 0 in programming language, then display error system is singular. If not, then we start with the row swapping. After the row swapping, we continue with Gaussian elimination. After that, we continue with forward substitution, then back substitution, then we print the computed flow rate.
Now I would like to explain about the flowchart of Gauss elimination method. For the C++, we will start the programming, display welcome message, follow it by input matrix A and vector B, form augmented matrix and display augmented matrix. So when the I equals to 0 to 2, it either find a pivot row, a swap row if needed, or display the matrix. So after the display matrix, the forward elimination will occur, then calculate the multiplier, update the rows, followed by back substitution and calculate the solution, and then it will display the solution vector x. Then the program will end. Now let's look at the MATLAB flowchart. It will start with the display welcome message, input matrix A and vector B. N is equivalent to length B. Initialize solution vector x, followed by form augmented matrix A over B. It will display augmented matrix where j equals to 1 to n minus 1. It's either find pivot row for P, a swap row if needed, or produce I equals to j plus 1 to n. After that it will calculate the multiplier m and update current row. And it also will display the matrix, followed by back substitution, and the display solution of vector x will produce, and then the program will end.
Now, this slide shows the overall program flow for solving a system of linear equations using algebraic decomposition, implemented in both C++ and MATLAB. In both implementations, the program begins by reading the required input data, including the coefficient matrix A and the measurement vector B, which together define the linear system AX equals B. The necessary matrix and vectors are then declared. Next, the matrices are initialized in the same way for both programs. The lower triangular matrix L is set as an identity matrix, while the upper triangular matrix U is initialized as a copy of matrix A. The LU decomposition process is then carried out using nested loops. For each pivot position, the elements below the pivot are eliminated by computing an elimination factor. This factor is stored in the corresponding position of matrix L, and the row of matrix U are updated using row operations. This process continues until the original matrix A is fully factorized into L and U. The main difference between the two implementations lies in the indexing. The C++ version uses zero-based indexing, while the MATLAB version follows one-based indexing. However, the computational logic and algorithm steps remain identical. After the decomposition is completed, forward substitution is applied to solve the equation Ly equals B, followed by backward substitution to solve Ux equals Y. Finally, the solution vector is displayed, representing the reconstructed muscle activation signals, and the program terminates.
Now let's look at the flowchart for the PLU decomposition method. For C++, we start by reading n, matrix A and vector B from complex_data.txt. Then we initialize matrices LP as identity and U is equal to A. Then we ask the system is k is less than n. If no, we continue with forward substitution, back substitution, and display solution x1, x2, and x3. Then we end the program. If k is less than n, we continue with pivot searching. After that, we ask the system is the max absolute value is equal to 0. If yes, we end the program. If no, we swap row P and row K in matrices U, P, and L. Then we continue with elimination SAP. Then we set k is equal to k plus 1. Then loop back to the question is k is less than 1. For MATLAB flowchart, it is identical to the C++ flowchart, but with different command.
This is the coding for scenario 1, which is a simple case regarding infusion pump calibration and dosage control. We attach the C++ coding screenshot and also MATLAB software coding screenshot. Now let's look at the result of scenario 1 simple case regarding infusion pump calibration and dosage control. Now I'm going to explain about the terminal output. We just attach the terminal output from C++ and MATLAB. This is the result from manual key-in, and this will be also discussed in the discussion part.
Now, these are the code for biomedical signal reconstruction in a multi-electrode EMG system for both C++ and MATLAB program. This slide shows the terminal output produced by the LU decomposition program for the EMG intermediate case. The program first prompts the user to select the input method. In this example, menu key in is selected and the coefficient matrix A and measurement vector B are entered based on the 3-electrode EMG system. After the input is provided, the program applies LU decomposition to factorize the coefficient matrix, followed by forward and backward substitution to solve the system of linear equations. The computed results are displayed as the muscle activation levels, where x equals to 2.5, y equals to 2.0, and z equals to 1.5. These values represent the reconstructed muscle activation signals corresponding to the recorded AMG measurements. The same output is obtained using both the C++ and MATLAB implementation, confirming the correctness and consistency of the algorithm.
So this is the results for scenario 3 complex case, fabrication of injectable hydrogels for cartilage repair. For on the left side is the C++ coding, and on the right side is the MATLAB coding. Then this is the terminal output after running the program with the example question in the input. We will get x1, x2, and x3 equal to 10.
Doctor, my name is Lim Hao Leong. Today I'm going to discuss about the calculation of the Gauss elimination, LO decomposition, and also PIO decomposition. Firstly, for the Gauss elimination, we first write the system in augmented matrix form. Then we perform forward elimination to remove the values below each pivot and convert the matrix into an upper triangular form. After that, we use back substitution to solve the equations from the last row upwards and obtain the values of x, y, z. In the LO decomposition, the coefficient matrix is factorized into a lower triangular matrix L and an upper triangular matrix U. We first solve the Ly equal to B using forward substitution and then solve Us equal to Y using back substitution. This two-step process gives the final values of x, y, and z. The manual calculation part ends with the PLU decomposition, which include a permutation matrix P to handle the row swapping for better stability. The matrix is written as PA equal to LU. We first solve Ly equal to PB using forward substitution, followed by Us equal to Y using back substitution. And this method ensures a stable solution and gives the final unknowns as well. Moving on, let's discuss the C++ and MATLAB programs used for the Gauss elimination. These two programs start by setting up the augmented matrix for the three unknowns. The coefficients and source vector are entered, and partial pivoting is applied to improve the stability. Then, forward elimination is used to remove the values below each pivot and convert the matrix into an upper triangular form. Finally, back substitution is performed from the last equation to the first to obtain the values of x, y, z. Besides that, we have LU decomposition. In this decomposition, the coefficient matrix is factorized into a lower triangular matrix L and an upper triangular matrix U. After forming A equal to LU, forward substitution process is used to solve Ly equal to B, followed by backward substitution to solve Us equal to Y. This two-step process gives the final values of the unknowns and is efficient when solving the systems with the same matrix but different right-hand sides. Last but not least, PLU decomposition further improves the numerical stability by introducing a permutation matrix P to account for row swapping, which gives the factorization PA equal to LU. In both C++ and MATLAB program, the program first searches for the suitable pivot elements and performs row exchange to avoid division by zero or very small numbers. The matrices L, U, and P are then formed through the elimination process. To solve the system, the right-hand side vector is first permuted to obtain PB. Forward substitution is applied to solve Ly equal to BB, followed by backward substitution to solve Us equal to Y. And finally, this approach combines the efficiency of LU decomposition with the stability of pivoting, resulting in accurate and reliable solution. This slide compares the Gauss elimination, LU decomposition, and PLU decomposition methods. First, for the Gauss elimination, this method solves a system by converting the augmented matrix into an upper triangular form using the forward elimination, and then finding the unknowns using the back substitution. It is quite simple and suitable for the small systems, but it may become unstable when the pivot is very small or zero, so pivoting is often needed. Next, LU decomposition factorizes the coefficient matrix into a lower triangular matrix L and an upper triangular matrix U, and this solution is obtained using the forward substitution followed by backward substitution. It is more efficiency and effective when solving the multiple system with the same matrix compared to Gauss elimination. Finally, PLU decompositions improves LU by adding a permutation matrix P to perform row swapping. This ensures better numerical stability and makes it the most robust method among the three methods. In conclusion, for simple systems, Gauss elimination is sufficient because it is easy to understand and has low computational cost. And MATLAB is very suitable due to its short and clear built-in matrix operations. For intermediate problems, LU decomposition is more efficient, especially when the same matrix is used with different right-hand side vectors, since the factorization is done only once. MATLAB is convenient with its LU function, while C++ is useful when more control over the algorithm is needed. For the compressed systems, PLU decomposition is the most reliable because pivoting improves the numerical stability. In such cases, C++ is preferred for large-scale or real-time application, whereas MATLAB is ideal for simulation and academic analysis.